Hi, I'm Chris Hansen from Dale and NBC, and today we're here to catch a
Wrong show!
Wrong show? Wait, oh my gosh guys, I'm so sorry. I'm Matt Gearhart from Calculus AB, and today I'll be showing you a shortened video reviewing and teaching the trials and tribulations that my fellow Calc classmates and I have gone through this year. Before we begin, there are a few details and context that you must know that truly have an informed view on calculus. If you don't know these details, just stop watching this video and learn them right now. Simply put, you need to remember all of your trig identities and the unit circle if you ever wish to be a successful calculus student. I mean, I don't know them, but that's not my problem anymore. Alright, now let's just assume that you remember and know all of that. We can now begin to look at actual calculus. And for this specific video, we will be looking at limits and derivatives. Before we begin, I think it's time for our calculus joke of the day. Are you ready, kids? Before we begin, I think it's time for our calculus joke of the day. Are you ready? Okay. Why is an electrical outlet called an outlet when you plug things into it? Wait, shouldn't it be called an inlet? No, because the limit exists. Wow, this is why I'm not paid anywhere near as much as Chris Hansen. Okay, back to limits. Basically, if the limit as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x are equal, then the limit exists. What this is saying is that the point f of a does not have to exist in order for the limit to exist. For example, look at this graph. On either side of the graph, the lines are approaching the same numerical value. Although there is a point discontinuity, the limit still exists. However, there are other examples of graphs in which it's not continuous, but yet the limit does not exist. Specifically in cases of jump discontinuities like this graph and infinite discontinuities in this graph. Speaking of continuity, let's discuss the definition of continuous. So, in order for f of x to be continuous, f of a has to exist. The limit of f of x as x approaches a have to exist, and the limit of f of x as x approaches a has to equal f of a. We use continuity a lot in calculus, specifically in the intermediate value theorem, or IVT for short. This theorem states if f of x is continuous at x equals a on the closed interval a to b, and n is any number between f of a and f of b, then there exists a number c between a and b such that f of c equals 0.
Alrighty guys, so I'm going to be taking on over here the fake Chris Hansen. We decided to fire him. His jokes were absolutely atrocious and his explaining was subpar. So we're going to be going over the definition of derivative using limits. So if you guys remember the limits from pre-calculus, one of the definitions that we use, the limit as h approaches 0 of f of x plus h minus f of x over h, that will give you the answer of f prime of x. The limit as h approaches 0, using a instead of x, in the first one, you would get the answer of f prime of a. And another solution to get f prime of a would be the limit as x approaches a of f of x minus f of a over x minus a. That will also give you f prime of a. So we're going to move on then to ARC, or average rate of change, versus IRC, or instantaneous rate of change. So average rate of change is going to be f of b minus f of a over b minus a, b being your second point and a being your first point, as you can see on this graph. And your instantaneous rate of change will be f prime of a, or the slope at that point. So right here we have our equation set up. This is our graph that we'll be using. So if you see the point f of a, f of b, located here and here, if you take the point f of b minus f of a over b minus a, that'll give you roughly the average rate of change from point A to point B. While if you take the slope at c, it will give you the instantaneous rate of change, since it's between the 2 points and it's the slope at that instant versus the slope change. Alrighty, so next we're going to be moving on to derivative rules. So how to take a derivative and the sort of rules and different methods behind that. So first one up, the power rule. So you'll often see equations like this where it's a function, or not a function, a variable raised to a certain number. So the way you're going to take the derivative of that, you're going to take the number that's in the exponent, bring it down to the front of the variable, multiply that variable by the number, and then take your exponent and subtract 1 from it. So a quick example, let's say it's x to the 8th. Your derivative would be 8x to the 7th, since you would bring down the power and subtract 1 from the power then. So next up we have the product rule. So sometimes you'll see two equations multiplied together and you want to take the derivative of those. So what you'll do is you're going to take the first equation, multiply by the derivative of the second equation, and then you're going to add that to the derivative of the first equation times the second equation. So let's say you have 7x times 14x or something like that. You would end up doing the 7x times 14 and then 14x times 7. Pretty simple. Next up, quotient rule. You'll also see equations divided by each other. So as I gave in the last one, 7x over 14x. Well, you could simplify this and then take the derivative. The best way to do it would be to multiply the bottom equation times the derivative of the top equation, and then subtract the derivative of the bottom equation times the top equation. And then you're going to put all that over the bottom equation squared. So for chain rule, the last one that we're going to be going over, you'll sometimes see a function inside of another function. So in this case, f of g of x. So what we're going to do for that, you're going to take this inside function right here, you're going to bring it to the outside and take the derivative of it, and then you're going to bring over the entire thing and just take the derivative of the f here. So if this was, or actually this is a great example of just f of g of x, you would just end up with f prime of g of x times g prime of x. Alrighty guys, so we're going to be going over exponential and natural log derivatives, as well as inverse functions derivatives and implicit differentiation. Starting off with the exponential and natural log derivations. So a lot of these you will have to memorize for the test because they aren't given to you, and they do come up really frequently. So the first one we're given is y is equal to e to the x. Derivative of that is just y is equal to e to the x. But the trick behind this is, let's say that this was e to the 2x, or e to x squared even. We'll use e to x squared. What you would do is you would bring down that x squared, take the derivative of the x squared, and then you would multiply that times e to the x squared. So really what you're doing is taking the basically multiplying the e by the derivative of the exponent, if that makes sense. The next one that we're given is y is equal to a to the x, so a being a constant. This would be a to the x times the natural log of a. So let's say it's 9 to the x, it would be 9 to the x times the natural log of 9. Next one, the natural log of x. The derivative of that is 1 over x. This also follows chain rule, where if it was natural log of x squared, it would be it would be 2x over x squared. Next up we have log, so the log of a of x, the derivative of that is 1 over x natural log of a. So a being constant, we'll use 9 again. So let's say it was log 9 of x. Your derivative will be 1 over x natural log of 9. Alrighty, moving on to inverse functions derivatives. So these you might have to memorize. So here we have f of x is equal to y. So the f prime of x would be equal to a. F inverse of y is equal to x. You really are just swapping those. And f inverse prime of y is 1 over a. Again, you're just swapping them, putting them over each other. Implicit differentiation. Let's say your equation is y is equal to xy plus x. So using dy dx instead of y prime or things like that, it would come out to dy dx is equal to x dy dx plus y plus 1. So we're going to be going through some trig derivatives as well as inverse trig derivatives. So starting off with the trig derivatives, a lot of these you guys will have to memorize for AP Calc for the test because they won't be given to you, and if you forget them it can often mess up your equations and really throw you off. So starting off, we have y sine of x. The derivative of that is going to be cosine of x. The derivative of the cosine of x equation is going to be negative sine of x. So when you're taking the derivative of cosine to get sine, really just cosine and sine will keep flip-flopping between them, but every time you go from cosine to sine, it's going to be the negative of whatever you had before. So next up, we have tangent of x. The derivative of that is going to be secant squared of x. And if you have secant of x, the derivative of that is going to be secant x tangent x. So these sort of work back into each other there. Alrighty, next one we have cosecant of x. The derivative of that is the negative cosecant of x cotangent x. So this is really similar to secant of x. The only difference is it's a negative and it's the co-version. So next we have the cotangent of x. That's going to be, the derivative of that is negative cosecant of x. And once again, this is very similar to the tangent of x. It's really the opposite version, or the secant, but since you have cotangent, it's cosecant, and it's negative since it's the co. Alrighty. So next, we're going to move on to inverse trig derivatives. The inverse trig derivative of sine to the negative first, or inverse sine of x, is 1 over the square root of 1 minus x squared. The derivative of the inverse of cosine of x is negative 1 over the square root of 1 minus x squared. And the derivative of tangent inverse of x is going to be 1 over 1 plus x squared. So when you're doing these, don't forget to do chain rule. So if you have a different powered exponent or x inside, don't forget to multiply by that like it was another function. So let's say that it was cosine inverse of 3x squared. Make sure that you guys bring out that 3x squared and take the derivative of it and multiply it into the original equation. So you would end up with negative 6x over 1 minus x squared. Alrighty guys, so right here we have MVT. If f of x is continuous on a to b and differentiable on a to b, then there exists at least one c between a and b such that f prime of x is equal to f of b minus f of a over b minus a. So IRC is equal to ARC.
Come here! Come here! Get down.
Your joke never made sense anyways.
Shut up! The spotlight is mine now! All mine! Hi guys, welcome back. It's Wreck Your Heart, aka Chris Hansen Jr. here. Okay, I just killed another newbie who wasn't anywhere near as good as me. Okay, I'm the best. Alright? At the close of this video, I'm going to be showing you an application of derivatives, specifically particle motion, okay? So particle motion all starts out with x of t, which stands for position of the particle, right? If you take the derivative of the position, you get v of t, which is equal to the velocity of the particle. If you take the derivative of the position again, or the second derivative, you'll get acceleration of the particle, which is symbolized as a of t. Specifically looking at these graphs, here we see that we have a position in which it's starting out to the left of origin here, and it's increasing constantly. Because this is increasing, the position is going to the right for the entire time, the velocity, we know, is constantly increasing in a positive way. Because this velocity is increasing, and because of what we know of the derivatives, we know that the acceleration in this case will always be at a constant time, and it'll never change no matter what. So this, guys, has been calculus in just a brief short few minutes. Sorry guys, I'm the best Chris Hansen, okay? I hope you all enjoy this video so much. Have a great day.